Okay, and now the question is, can we extend this? I mean, now up to now we haven't got any new result, but the question is whether we can now imitate this or adapt this to the situation where we want to calculate the distribution of something more complicated. Okay, and so let us see what we can do or how far we can go. Maybe let us try to do the same. Start in the same way as before, and of course it's clear if we are here we will have a problem, but okay, we have to think whether we can deal with it. Okay, so we want to do the same now for not X, but for this feature matrix, which is this sigma. We take this W, we have to normalize it by the square root of P times X, which is a M times N matrix. Okay, so this is N times P, this is M times P, and then okay, this is of this nature. And now of course we look on the resolvent of this guy. So maybe, and so maybe now what I now denote by the resolvent. So this is the resolvent of this. So this will be 1 over N F transpose minus Z times the identity. Okay, and the identity is here an M by M matrix. So the resolvent is now M times M, because now we have M times N, not P times N. Okay, so the inverse of this is the resolvent, and the Stieltjes transform is the expectation of the trace of this. And we want to see, can we derive an equation for this, which of course in the end should be the quartic, the equation of fourth order, which we have in our theorem. So I mean the point is we can, or we should be able to do it, but how do we get there? Okay, so let us start in the same way as before. So we have 1 plus Z times the Stieltjes transform, and then by just using the fact that if I multiply this with just the thing without the inverse, I get the identity, and taking the expectation and the trace, I get exactly that this is the expectation of the trace. And now I get my matrix here in this term. So I get here the trace of 1 over N F transpose times the resolvent and the expectation of the whole thing. And as before, of course, I can develop it in this form, and maybe the entries of my matrix F I denote by little f, so the entries are Fij's. And then, of course, this here, as before, is the same as 1 divided by N times M. I mean, the P is now an M, and I have the sum over Ij, and I take the expectation of, and I write this now again as this is a product of this matrix with this matrix, and I write it in terms of the entries. So I get here the little Fij, and here I get just this matrix Ft R of Z entry Ij. Okay, and again, so you see I just have replaced the entries. I have the capital X by the capital F, and the entries Xij are now the Fij's. And again, I have here now, as before, an expectation of an entry of my matrix with a function of all the entries. Okay, but now of course the problem is this Fij is now not a Gaussian matrix anymore, and the Fij's are not independent. I mean, the entries of X, they were all this was a standard Gaussian matrix, so the entries were all independent and all Gaussians, and for this we had this nice Stein's identity, which tells us that if I multiply with one of the variables, a function of all the variables, it has the effect of taking the derivative. Okay, but this depended, of course, on the fact that the Xij had a very specific distribution. Okay, and this is now, of course, not the case anymore, because, I mean, the entries of F, they are multiplications of independent guys, but, I mean, they are not independent anymore, and then at the end, even we take some non-linearity. So it's not so clear what this is. Okay, but so the question is, do we still have a replacement of this Stein's identity? Is there a more general version which would also cover this? Because I mean, this was a nice, I mean, this was a quite powerful tool. So if we could apply this in more general situations, this would be good. Okay, and this is actually the case. So I mean, we still can do something, but it's of course getting more complicated. And in particular, first we should really understand what is this generalization of this Stein's identity. And this is this cumulant expansion. Yeah, okay, so maybe let me write it down just. So the question which we have to deal with if we want to continue in this direction, so do we still have a version of Stein's identity for such a general case? And I mean, this should be general in this that we just have some random variables with arbitrary distribution, because I mean, we will get here quite complex distributions. So in principle, we should have something which is arbitrary. Good, okay, and maybe, yeah, to see what we get or what we can hope for is maybe we should look on a one-dimensional case. Yeah, so what is Stein's identity telling us then? So recall the one-dimensional case. So this means, so t, we only have one variable, and this has to be a Gauss variable. So independence is there not an issue. It's really the question whether it's Gaussian or not, the distribution. So if t, so this is a standard Gauss distribution, then this Stein's identity says that if I take the expectation of my variable times a function of my variable, so under the expectation, this is the same as just taking the expectation of the derivative of the function. So the effect of multiplying with t has the effect of taking the derivative. So this is the expectation of h prime of t. And essentially this was just partial integration and using the fact that if I differentiate the density of the Gaussian distribution, I get a factor t out. So differentiation produces me a factor t somehow. Good, okay, but of course this is a very specific property of the Gauss distribution. Okay, and now for a general case, of course this will not be true anymore. So we have to generalize it somehow. And so one can, for a general distribution, if t has now a general distribution, I mean try to keep somehow the spirit of this by either, I mean, okay, this equation will not be true in this form anymore, but we can try to keep one side of the equation and check what do we have to do with the other. So there are essentially two possibilities. So we can try to keep the right-hand side of this equation, but then of course we have to change the left-hand side to something depending on the distribution. So this means I still want, so I want to keep this, so I want to do something here which has the effect of giving me the derivative here. And it won't be multiplication with t anymore, but in general, usually I can find some other function here of t which has this effect. Okay. Good, and this is usually called a score function. So this is the context of score functions where you do this. So this is an important thing which in statistics very often shows up. So this is replacing this guy here by a score function, a more complicated function which depends on the distribution. For the Gauss distributions it's this one. For other distributions I have to take here other things. I multiply and they still have the effect of this. Good. Okay, so this is interesting direction. This can be done, but of course that's not what we really need, because I mean we don't really have the freedom of choosing this here. So we have to multiply with the variable. So we should keep this side here and see what happens on the other side. So the other possibility, and that's the one which we want to follow here, is we keep the left-hand side, but then of course we have to change the right-hand side. Okay, so we still want to multiply with our variable, and the question is what effect does it have, or can we rewrite it in a form which has something to do with derivatives? Okay, and this is then what usually goes under the name of cumulant expansions, and that's what we want to do here. Okay, and so that's what the following I want to talk about. So I mean, we just have to understand this before we really can continue. Good. Okay, and I mean, we should check to get an idea. And in order to get an idea, I will now try to see what the effect of the multiplication with my variable is by applying it to specific functions h. I mean, it should be something which is true for all h's, but I mean, it's okay. In order to see what it should be, it's good to choose specific h's, specific functions on which you tested what it is, and in particular, those functions should have simple derivatives, because I mean, we expect that we get derivatives. It should be related with derivatives, so we should have functions for which we know, maybe not only the first, but all derivatives. And what are the easiest, or what are the functions of which all derivatives are very easy? It's exponential functions. So we check it on exponential functions, and on the other hand, exponential functions we can use for producing by linear combinations, and going to the limit, we can produce more or less every function, just by Fourier analysis, Fourier decomposition. So in principle, if we understand what here happens if I know it for exponential functions, then essentially I understand it for all of them. So that's what I want to do. I want to see whether I can get this formula if I choose exponential functions for the h's. And then of course I should get, on the other hand, I should get something which is linear in derivatives of my function, such that I can extend this by linearity. And again, I do this in a one-dimensional case, but actually this also works in a multi-dimensional case. So the motivation is in a one-dimensional case, but then I will formulate afterwards the statement in a multi-dimensional case, which we really need. Good, so let us check or try to start from the left-hand side for specific functions and try to arrive somehow on a version of the right-hand side. So we consider now specific functions h's which depend on the parameter s, so they are functions of t, and they are exponential functions, and I put an I here. So it's really like in a Fourier transform. I mean, it's okay. Without the I, it would be essentially if I take the exponential expectation, it would be the moment generating function, which we already had before. And with the I, it's more or less the Fourier transform. Okay, but anyhow, so I take these functions here. So for each s, I mean, I need it not only for one function, but for sufficiently many s, and then by Fourier transform, I can write more or less every function as a linear combination of guys like this, or a continuous version of this. Good. Okay. So I take those guys, and then I start from the left-hand side, and let's see where we get. Okay. So then I have the expectation. I want to multiply this function hs of t with the argument t. Under the expectation, of course. I mean, without the expectation, of course, I cannot say anything. But under the expectations, those things happen. So I have here t times e to the I ts. S is a parameter. Okay, and now the question is, I mean, how can I produce this t somehow out of my function in a way which I can deal with? And of course, if I have it like this, I mean, I can get the t down here by taking the derivative with respect to this parameter s. Okay, so I can say this is the same as the expectation of, okay, I should get also minus I, and then the derivative with respect to s of e to the I ts. Okay, so if I take this derivative, I will get down the t, but I will also get down the I. So I mean, I cancel this with this minus I here. Okay, so I get this. But of course, this derivative doesn't help me so much, because I mean the derivatives which I would like to have on this side would be derivatives with respect to t. Okay, this here is just an intermediate step, and now I'm writing this. Yeah, okay, so in principle, I mean, I can exchange this. So this is the derivative with respect to s of the expectation of this guy here. And now I also want to have back somehow my guy here without the derivative, and this means, okay, I take the derivative of this guy, but I also divide by it so that I get it back. And this tells me that I write this. Let me write it down. I mean, maybe it's a bit strange, but anyhow. So I take actually not this expo. Here I have the derivative of the expectation of this guy, but now I take the derivative of the log of the expectation of this guy. So this is this. Okay. And why do I take the expectation of the log? Because if I take the derivative of the log of a function, then I get the derivative of this function times the derivative of the log, which means I have also to divide by this function. So I get the derivative of what I have here, but then I also get divided by this guy here, which means I should multiply it again with this in order not to have to make x-text. So I have here the expectation of e to the its. Yeah, I mean this cancels the extra term which I get because I have here the log. Good. Okay, and now I have derivatives with respect to s, and now I just write this here as a power series. I mean this is a function in s. I mean s is only parameter, but I consider it as a function in s because I do derivatives. So this is somehow a function in s, and I write it as a power series. Okay, and the coefficients which I get in this power series, they are very important guys, and they are called cumulants. Okay, I mean they are just appearing here as the coefficients in this log. So I say this here has a power series expansion, and I write it in a sense in a exponential way. So I put explicitly L factorial here. I mean, it's a Taylor series expansion type. I have here the argument, and the argument is here, let's say, is to the L. I mean, I take the expectation over t. So the t is gone. I mean, I take the expectation over this. So the whole thing here is a function of s. Or maybe I say the argument is I times s. So I put here the I explicitly. So it's this one, and so I start here from 1 to infinity. Yeah, because at 0, this thing is 0. If s is equal to 0, then I get here 1, and the log of 1 is 0. So there's no 0th term. And so I get terms starting at the powers of s. And those guys, I just denote them by kappa L, and I call them cumulants. Okay, so this equation here is a definition of those guys here. So this is the definition. But those will be the important guys which we have to understand better later. So definition of the kappa Ls. Good, but now if I'm here, then I can do the derivative here applied on this guy here. And so let me check what I have now. So I have now the minus I. Then, okay, I mean this sum I can take out. So let me put it at the beginning. This is the sum L from 1 to infinity. Then I have the kappa Ls. Okay, and then I do the derivative. I mean the s is now only here. So I do the derivative of this guy with respect to s. So an L comes down, and here I get power which is 1 less. If L comes down, this L factorial will be changed to L minus 1 factorial. So I have here L minus 1 factorial, and I still also get 1i from the derivative, and then I'm left with is to the L minus 1, and I still have this expectation here, its. Yeah, which is of course also function of s. But this derivative here only applied to this one here. Okay, so I have now this thing. Yeah, and now this expectation only applies to t. That's the expectation over t. So I can actually move this out here and then see what I have in the inner, what I have there. Yeah? And I mean, we should what do I want? In the end, I want something which is acting on my original function by maybe using derivatives or something like this, a linear operator. Huh? So I mean, and I should have an expectation. Huh? I should have an expectation around everything, but that's good. I have here an expectation, so I have here the expectation of, and of course this I, with this I gives exactly minus, so this goes away. This fits together. So I have now here the sum, and because I have here maybe the L minus 1, I shifting this by 1, so now what was before L minus 1, I call it now L. This means what this L here becomes now an L plus 1. So I write this now as a sum where I'm shifting the index, and then I'm summing from 0 to infinity. But then I have here L plus 1, but here I have L factorial, and here I have is to the power L. Yeah, and then here I have the e to the its. So good. Okay. Yeah, and now I want to see that this is applying something onto this function, because that's the function from which we started. That's our function hs. Okay, and now you see I'm multiplying here with powers of s, and this is actually taking the derivative with respect to t now of this guy, because if I take derivative with respect to t, I'm getting down the s. And I have those guys here. So these guys are just the effect of having taken derivatives, but now of all orders, because I'm summing over those guys. So yeah, this here, this thing here, this is the nth derivative, but with respect to t of e to the its. Let me see, is this okay? Yeah, I mean each derivative brings down an I times s. Okay, and I have here I times s to the power L. So I'm doing L derivatives, which is nothing else than our function, the Lth derivative of t. So you see, I mean, I really, yeah, it's a strange way. I mean, I start with doing derivative with respect to s, but I'm somehow able to change this into derivatives with respect to t, and that's what I want. Yeah, good. Okay, so what I have in the end is the expectation of this sum L from 0 to infinity kappa L plus 1 divided by L factorial. And of my original function, I take the Lth derivative. Okay, and so you see the effect of multiplying with t on my function hs has the effect that I'm taking linear combinations with those coefficients of taking derivatives of all orders. Okay, and now, of course, I mean, if I now do Fourier decomposition, now if I write a function f as an integral over hs's, then of course this here is linear, and I mean this will then also go over two arbitrary functions. Okay, so maybe that's what I then formulate in the following. So just what we saw here. I mean, essentially we have a proof here of this statement. Okay, let's call it a lemma. One-dimensional case. So let t be a random variable. Okay, and maybe such that all moments exists. Okay, so that we can take, for example, polynomials for the h's. Okay, and then, then first we define, we have to define maybe officially those kappas, and we define them exactly by this equation there. So then we define these kappas, and they are called cumulants, kappa L. So just by this equation, so I take the, I take the Fourier transform essentially of my distribution. So this is the expectation of e to the I ts. So that's a function in S. T is my variable. I take the expectation with respect to this. Yeah, okay. And this is I. This is the Fourier transform. I mean, in probabilistic terms, this is the characteristic function of the variable, which is the Fourier transform of the density. Okay. Okay. But then of this guy, I take the logarithm, and then I expand this logarithm in a power series in S, and the coefficients there I call cumulants. So this is then, as I did it there, the sum from 1 up to infinity of some coefficients, which I denote by kappa L, divided by L factorial is to the L. Okay, so that's just the definition of the cumulants. Okay, but then the point is that those guys here are showing up exactly in the generalization of this Stein's identity. So now, I mean, this is definition, but now the statement is, so and for a smooth function h from R to R, we have that if I take just the equation there, if I take the expectation of t multiplied with this function, then this has the same effect as summing over L from 0 to infinity of the L plus first cumulant divided by L factorial. And then, okay, maybe I write the expectation here, taking the expectation of HLT, where this is the Lth derivative. Good. Okay. So that's more or less what we saw here. And maybe, before I go multidimensional, maybe we should just pause for a moment and see that this really is in the case of the Gauss distribution gives the right thing, because there we know what we should get. There actually we should only have one derivative, but this of course is correct because the Fourier transform of a Gauss distribution has a very simple form. So, but maybe it's good to think about this. Yeah, so the remark is that this is really consistent with what we already know in the Gaussian case. This is consistent with Stein's identity. So namely, if T is a standard Gauss, then, I mean, we know what the Fourier transform is. Then we have, so the expectation of e to the I ts. So the Fourier transform of this, this is just e to the minus s squared divided by 2. I mean, I think everybody knows this, but on the other hand, I mean, I actually did this even when we looked on our concentration things, and then we also, I mean, we took this without the I. This was the moment generating function without the I. And I'm, of course, for the calculation, it doesn't matter whether I have an I there or not. And then, I mean, we got this result, but maybe it was exploding. Now, because of the I, we get the minus here. Okay, so that's the Fourier transform of the, so maybe if you want to see the calculation, I did this back in 2011 in the manuscript. But now, of course, the logarithm, because now if the Fourier transform is of this exponential form, the logarithm of this is very easy. And you see now exactly that the power series expansion is even easier because there's only one power there. So the logarithm of the exponential of the expectation of e to the I ts. So this is the logarithm of this, which is just minus s squared divided by 2. Okay, and this means, of course, this is the power series expansion of this very explicitly. This means this is a power series expansion where only the quadratic term is there, and the quadratic term, yeah, I mean we should, so this corresponds to L equal to 2. For L equal to 2, I get s squared. I get here the I squared. I also get the minus, and I get here the 2 factorial. I get the 2 there. So this means actually the coefficients, the kappa 2, which I have here, is just 1. So this tells me the second cumulant of Gauss is 1, and all the others are 0. So this means kappa 2 is equal to 1. and kappa L is equal to 0 for all L which are not equal to 2. Okay, and then of course, then this statement here reduces just, okay, I'm summing now only over the case where I have here 2, which means L equal to 1. Okay, and then of course divided by 1, and here I just have the first derivative, and that's exactly Stein's identity. So then the expectation, I mean then this 7.3, this general cumulant expansion tells me that the expectation of t times h of t is, yeah, it should be kappa 2 divided by 1 factorial, the expectation of h prime of t, which is just the expectation of the derivative. Okay, so this is consistent, and this is really a generalization. Okay, so only in the Gauss case, the effect of multiplying with t only gives me the first derivative. Otherwise, it's all derivatives are involved, but the weight with them with which they are involved are those cumulants. So this means it's good to understand the cumulants, and in particular, if you have situations which maybe are not so far from Gauss, maybe you can see that those guys are small. If you can make estimates on them, then you still should be able to get meaningful results. Good, but of course, I mean, this is the one-dimensional case, and what we need is of course the multidimensional one, because we really, I mean, we have to calculate with all the entries of our matrix. So it's really, we have the distribution of all the entries of our matrix, of the F matrix, and then we have to see what was the analog of this. And actually, I mean, there's the analog of this in higher dimensions works in the same way. Okay, so I'm writing it down now, but essentially you could, I mean, the crucial calculation which I did at the beginning, you could also do this for the multidimensional exponential functions, and then it's more or less the same. So it's really, it's getting more complicated to write it down because you have all the indices and so, but in principle it's the same. So let me just give you the statement, and of course the definition of the cumulants in this higher dimensional case, because we also need this. Yeah, so maybe now let me officially define the cumulants, not putting it into the theorem, but I mean, they are so important that maybe we should put them as an official definition. So now I consider a multidimensional version, so I have a collection of random variables, let's say t1 up to tk. I mean, later on they will be indexed by ij, by double indices, because I put them into a matrix, but of course this doesn't play a role for this here. So it's just a finite number of random variables. And I mean, there's now no assumption that they should be independent or they should be Gaussian or whatever. They could be quite arbitrary. And then, yeah, I mean, first of all, one defines the characteristic function or the Fourier transform of them. So that's the thing as before. So there, I mean, usually it's called characteristic function. Yeah, but this is the Fourier transform of the density. So it has the Fourier transform of their density function. So what is this? Yeah, so this is the expectation of, and I take just the multidimensional Fourier transform. So I take e to the I, and now I have the variables t1 up to tk, and I just multiply them with parameters s1 up to sk. And I consider this as a function of the s's. So I have here t1 times s1 plus t2 times s2 plus tk times sk. Or you could say I take the vector of the t's and I take the inner product with the vector of the s's. And I consider this as a function of s. So you can say I have a function in r to the k, and this thing here is also a function in r to the k. Okay, so I take this expectation over the t's, maybe if I write it explicitly, so this is the integral over k. If I have a density, so this is e to the I t1 s1 plus tk sk multiplied with the density, probability density distribution of the t's, d t1 up to d tk. Okay, so that's the characteristic function. I mean that's standard, of course. That's the characteristic function of the Fourier transform. But now the interesting thing we want is the logarithm of this. Okay, and then the coefficients in the power series expansion of this are called cumulants. So this here are the characteristic functions. And of course, you see, if you multiply this out, essentially this will be, if you do a power series expansion of this, the coefficients there will be the moments of your variables. Okay. But now, instead of the moments, instead of doing the power series expansion of this function, we do the power series expansion of the logarithm of this, and then we get other coefficients, and we call them cumulants. So this is now a definition here. So the cumulants of my variables, t1 up to tk, are defined as coefficients in the power series expansion of the logarithm of the characteristic function. So I take the expectation, I take the logarithm of what I had here, the expectation of e to the I t1 s1 plus tk sk. So this is a function in the S's. If I take the logarithm, it's another function in the S's. Okay, and I do the power series expansion. And this is, of course, a multivariate power series. So I mean, I get all possibilities of having products of the various S's. And so, I mean, I'm writing it as a sum, and I have here the kappas. And actually, I mean, what I'm writing here as L are now multi-indices. And here I don't want to be too specific because it's a bit confusing. So I write here kappa L, I t to the L. I'm summing over L, and L are multi-indices. So this means, I have, it tells me I have L1 S1s, I have L2 S2s, and so on, and I have to interpret this. This is something which depends on all those indices, and this L factorial is the product of the corresponding guys, and here I have, this is actually T1 to the L1 times T2 to the L2. So I mean, that's the standard thing you do if you do the multidimensional Taylor expansion. But okay, maybe it's better not to be too specific about this because it's somehow just confusing. Okay, so but actually, I mean, the cumulants which we have here are actually also multidimensional objects. So they are indexed by not just one L, but this is really a collection of numbers, depending on the variables which you have. So in principle, it's better to write the kappa as something which depends on arguments, saying which random variable you have. So maybe it's good to write it as ti1, ti2, and so on up to tir. So it's an object which you essentially have for all i1, i2, ir. Okay, and maybe it's it's better to give you the analog of this cumulant expansion, because this reveals in the end much better the nature of those cumulants. I mean, this definition, of course, they are defined now, and now it's a statement which one has to prove that I have the analog of this, but then this formula is really telling you much better what the cumulants are. Maybe we'll have a look later, but maybe let me first write down the analog of this in the multidimensional case. Okay, so that's our cumulant expansion. So the same setting as before. I have variables, random variables, a collection of random variables and let kappa be their cumulants. And let kappa, which are defined by this power series expansion of the logarithm of the characteristic function. And then again we have a statement like this. So then we have again for nice functions h, but h is now of course a function of all my variables. So it's a function on r to the k. So h from r to the k to r. Yeah. So then we have that if I take now the expectation and I'm multiplying my function with one of the variables. And of course, as before, I can choose any of my variables. So I'm multiplying here with ta, my function, which is a function of all the variables. Yeah, and so what do I get there? I get, as here, I get a sum. I get a couple of sums. And then I have to sum over the cumulants. But now I have to specify, I mean, the cumulant of which variable, and then I have to take derivatives. So I also have to take the cumulants of those. So I have here the cumulant of ti. The ti is the one which I have here. Okay, and then I have to sum over all possibilities for taking derivatives, and I will now sum over taking derivatives, all kind of partial derivatives for all possibilities. And they are weighted with something, namely with the cumulants, where I put here ti1 up to til. Okay, and I'm summing here over all else, starting from 1 and over all possibilities of the I1s up to IL. The I is fixed. The I is the one corresponding to the variable I have here. But here I have the freedom of summing over all of them. So I1 up to IL, they are all running from 1 up to k. I divide this here by L factorial. And then I have here the expectation. And now I take partial derivatives of my function. And the partial derivative with respect to the variables which showed up here. So I take the derivative with I1 up to IL of my function h of t1 up to tk. Okay. So I mean, it's of course it's a horrendous formula, but it has some structure. Okay, and in principle, I mean, in principle, all derivatives show up. Of course, I mean, if I have to know all derivatives of all the expectation of all partial derivatives, maybe that's information which is hard to get. But I mean, if I have enough information about here, then maybe many terms are 0 or very small, and then maybe I don't need so much information. And that's of course the hope, how I could use this formula. Yeah, I mean, it's like Taylor formula. Of course, in principle, it tells you everything, but of course, you must be able to calculate what are the important terms in this expansion. And here it's the same. So it really depends on the concrete application, whether you can use it or not, whether you have enough information about the things showing up here. In particular, you should have information about the cumulants. Okay, so this means we should understand the cumulants somehow a bit better. Okay, and maybe so I want to give you a bit, maybe a more combinatorial feeling of what cumulants are. I mean, they are just defined here in a more analytic way. You have a power series expansion, and you call the coefficients their cumulants. So that's an analytic way of doing it. But on the other hand, I mean, of course, you see that what we are doing here is we are relating the coefficients in the characteristic function with the coefficients in the logarithm of the characteristic function. The coefficients in the characteristic function, they are the moments. Okay, and the cumulants are defined as the guys in the power series expansion of the logarithm. So this means the cumulants should be some functions of the moments and the other way around. And of course, this here tells us which kind of functions, but in a way which is not so easy to see. And actually, there's a very nice combinatorial connection between those guys, and this combinatorial connection is more or less hidden in this formula here. I mean, this is really a formula which has a much more combinatorial meaning. And so maybe I want to talk a little bit about this, and maybe just again do it first, start in a case k equal to 1. So just in this form here, to get a feeling what really what is the relation between moments and cumulants, and what is a combinatorial formula for this, which is just a reformulation of what we have here, but maybe a very useful reformulation. Good, so I want to talk a little bit about this. Because if we, because usually it's not so easy to get concrete information about cumulants out of their definition as the power series expansion of the logarithm of the exponential function. So you need other ways of understanding them. That's the crucial thing. I think in principle we can forget about this formula here. And if you like, you can also take this here as a definition of the cumulants, because in principle it's equivalent to this here. And in this, I mean, of course, this becomes useful. I mean, or to make the contact with moments, of course, we can choose now specific function h, namely just products of the variables, because then we just have here moments. Then we have here relations between the moments, which also involve the cumulants. So I mean, the proof essentially of this formula was for working on the exponential functions, but I mean, to get some concrete information out of it, it's better to look on monomials, and because then it gives you a relation between moments. Okay, but let us start with, okay, I mean, I can choose for my h's simple functions, and of course I can start with the simplest one, which is just a constant function 1. Okay, so it should be true for the constant function 1. Is there anything anything interesting? And of course on this side I have the derivatives of my function, and of course derivatives of a constant function are 0. So if I have derivatives here, they are not there, but actually you should see that I also have the term L equal to 0, which means that's a term where I don't have a derivative. Then I just have the function here, and here I only have, I mean, if L is equal to 0, this means those guys are not here, and I just have the cumulant of Ti. So this means no derivatives, but actually there is a constant term there. So the only L equal to 0 contributes, and then this formula tells me that the expectation of Ti, which of course is the same as the expectation of Ti times 1, and then I'm here with h equal to 1, and then the other side tells me the L equal to 0 term, which means there are no i's to sum over, so it's just a k of Ti, and I have to divide by 0 factorial, which is 1, and then I'm left with the expectation of, okay, no partial things there, just h. So it's just the expectation of 1. And of course the expectation of 1 is equal to 1, so this here is just kappa of Ti. Okay, so this tells me this cumulant of first order is just the same as the expectation. So the first cumulant is the same as the first moment. Good, okay, but it's more interesting if I now go on. So now I take for my function T1 of Tk, let's say just one of the variables, so just one Tj. So that if I multiply this with a Ti, I have the second moment Ti Tj. But what do I get then? So I have then the expectation of Ti times Tj, the second moment. And what is this formula telling me? I mean, I can now on this side, I can now take no derivative, that's okay. I can also take one derivative, that's also okay. But if I take higher derivatives, they are 0. So this means in this sum, I only have the L equal to 0 and the L equal to 1 term. Good, and the L, what is the L equal to 0 term? That's again the term as before. So I have the kappa of Ti divided by 0 factorial, and then it's getting multiplied just with the function itself, just with the expectation of the h. This is just Tj. Here I have the Ti, this is corresponding to this, and here I have the Tj, this is corresponding to this. So this is the L equal to 0 term. Okay, but then I also get the L equal to 1 term, and there I'm summing over i's. So I'm summing over the I1s. and I get a kappa of, yeah, now I have the Ti, and then I also get the T of the I1. Okay, and then I take the expectation and I take the derivative with respect to this variable here. So I take the derivative with respect to I1 of my function h, which is Tj. Yeah, so that's the L equal to 1 term. And I mean, that's actually okay, summing over the I1. But now, of course, we see if I take the derivative of the variable Tj with respect to the variable I1, then of course this is just delta. I mean, this is only 1, this is exactly 1 if I1 is equal to j, and otherwise it is 0. I mean, if I have my variables, then the partial derivative with respect to the variables, okay, for each variable, I just get the delta function. So if, and of course the expectation, so I mean this is either 0 or 1, and then the expectation is also 0 or 1. So I get delta of I1 j. So only if I1 is equal to j, then I take the derivative of Tj with respect to Tj, which is 1, and otherwise I take the derivative of Tj with respect to other variables, which is 0. Okay, and then of course the sum over I1 only gives exactly the contribution j. So only the I1 equal to j is surviving here. Okay, and so this means what I have here is the first order term, kappa Ti. But now maybe if I want to write this totally in terms of kappas, the expectation of Tj, the first moment, I already know that this is the same as kappa. So I can also write this here as kappa of Tj. Yeah, okay, and then from here in this sum, only the term I1 equal to j survives, and then I just have kappa of Ti, comma Tj. Okay, and so you see the second moment is given in terms of first and second order cumulants. And maybe this has a nice, maybe a diagrammatic interpretation, which here still looks maybe a little bit silly or maybe easy. So the expectation of Ti, Tj, so this is, let me write it again. This is the cumulant of Ti, Tj, plus the cumulant of Ti times the cumulant of Tj. And if you think about, if you want to draw this in diagrammatic terms, essentially you have two arguments, and what you have to do on this side is you have to take possibility, you have to take products of kappas, and you are distributing your arguments. I mean, here you have the arguments I and j. You have only two arguments, but you can say, okay, I mean, I keep them together and they should go into one kappa. This is this guy here. Or I separate them, so each of them should go into a different kappa. This is this term. So I have a first order kappa of Ti times a first order kappa of Tj. So at the moment I'm getting by summing over those two possibilities, and that's the only two possibilities for how I can split the two arguments into groups. Okay, and I mean, of course this goes on, but that's the point of explaining it like this, but that this is also true in a more general case. And so maybe we could also look on the third order case for the third moment, where I take now for the h a product of two of the t's. And then if I multiply it with the Ti, I have a third order. So I should get a formula for the third order, for the third order moment. So I take of h, I take T1 up to Tk. This is just now the variable j times the variable r, for any choice of j and r. So I'm free to choose this. Yeah, and then, so what does this formula, this cumulant expansion, tell me? So I'm multiplying Ti with my function, so I have Ti times Tj times Tr, and then here in my sum, of course I'm running now over L equal to 0, 1 and 2, because I can take derivatives up to second order. Higher derivatives are 0. So this means I get terms corresponding to this, and again the first order term is just I take the cumulant of Ti and I multiply it with the expectation of no derivatives and just my function, which is the expectation of tj tr. Then I get for L equal to 1, I'm summing over I1, and I get the cumulant of this ti, but then also of the second argument, ti1, over which I sum, and I get the expectation, and in the expectation I'm taking the derivative with respect to this guy. So the partial derivative with respect to the I1 variable of my function, which is tj tr. Yeah, okay, and then I also get the third order term, where I'm summing over 2 of my variables, and then I get, okay, I get this 1 over L factorial. So in this case I get a 1 over 2 of kappa, and I have here ti, and then I have here ti1 and ti2, and I take the expectation of, yeah, the two partial derivatives. I mean, partial derivative with respect to I1 and partial derivative with respect to I2 of tj tr. Good. Okay, and now, okay, yeah, we have to work this out. And of course here, I mean, yeah, this partial derivative here, I have here a product of two variables. I take the derivative with respect to one of them, so I get the product. I take the derivative of this times this plus the other way around, and again, I mean, the indices must fit. If I take the derivative of the tj with respect to the I1 variable, the j must be equal to I1. Okay, so this means what I have here is delta I1 j, and then I'm left with the tr. Or I take the derivative of the tr, and then the I1 must be equal to r, and then I'm left with the tj. Okay, and this means I'm summing over I1. So this means here I'm getting this is I1. Okay, so the I1 must be j, and here the I1 must be equal to r. Okay. Yeah, and here in this case I'm taking two derivatives. So one of them, this cancels the first variable, and the other cancels the second one. But I mean this I1 can either do this or this, and then this has to the other way around. So I'm getting actually two terms here. So this here, this is either the I1 acts on the j, then it must be equal to this, and then the I2 has to act on this one, and then the I2 must be equal to r. Or it could be the other way around, that namely the I1 acts on the r, then delta I1 must be equal to r, and then the second derivative must act on this, then the I2 must be equal to j. Okay, so I get those terms, and now I can multiply this out, or collect all the terms. And see what I have. I mean, it's a little bit bothering that I have this 1/2, which is in combinatorial formulas. It's not so nice to have it there, but actually we see that it will go away. And we have a nice combinatorial formula like this without any non-integer coefficients. So the L equal to 0 term, I mean, this is clear. So this is kappa of ti times the expectation of tj tr. Okay, and then I have the L equal to 1 terms, and I mean I have two of them, because I'm summing those two guys. So I have the first term is the I, where the I1 is equal to j, and then the summation over I1 gives me exactly the j term. So this is kappa of ti, and then the I1 has to be equal to j, and I'm left with the other variable, which is tr. Or I have the other term, where actually the I1 has to be equal to r. So I have here the tr, and then I'm left in the expectation with the other guy, with the tj. Okay, and then the second order term, which is because of this 1/2 might look not so nice. Actually, so what do I have there? I have the sum of two terms here. I also get two terms here, which is good because this will cancel this 1/2 away in the end. So namely, I have 1/2, I have kappa of, first argument is always ti, and now the second and the third argument are either the j or the r in one or the other order. I mean the two terms. So the first one gives the tj, tr, and then the identity of the expectation of 1, which is 1, so the expectation is not there anymore, plus kappa, and then it's the other way around, ti, tr, tj. Okay, and now one can check that actually these kappas, I mean, the difference between this and this is just that here the arguments are exchanged and they are actually the same, because I mean everything commutes here. So this here is actually just 2 times kappa of ti, tj, tr, and then this 2 goes with this 1/2 away. So this means I just have a sum over terms and all the coefficients are just equal to 1, which is a nice combinatorial formula. If I would have 1 over some factorials in those formulas, this wouldn't be so nice. So I mean, those factorials are showing up in this formula, but in the end, if you really work it out, here, they all disappear. Okay, and so I mean, what I have now here, so maybe, so I have now I have essentially 5 terms because I can replace the expectation again by the kappa. We know the first moment, kappa, is the same as the first kappa. So this is the kappa, and this is the kappa. And the second moment is the sum of the second cumulant plus another term, which is the product of 2 first order. So this can be replaced by a sum of 2 guys. So in the end, I have here 5 terms. 1, 2, 3, and this gives me 2 terms. So I have 5 terms, and this 5 terms, so maybe I write it here. So what I have kappa of t1, tj, tr. So this is this last term here. Okay, and this again, if I want to draw it in a pictorial way, I have my 3 variables ti, tj, and tr, and I should decide, following the philosophy which I gave you before, how I distribute this onto kappa. So I could say, okay, I take them all together and they go into 1 kappa. That's exactly this term. Okay, then what do I have? I have also this term here, where this here, I mean here there are 2 possibilities, but maybe let me first take the kappa of ti, and then this expectation is the kappa of tj, tr, plus another term, which I put down later. But here I can say, okay, now I distribute the ti into a kappa, so this is alone, and I take the other 2 together, and I put them into another kappa. So that's the interpretation of half of this term. Okay, then I have this and this term, where I replace the expectation by the kappa. So maybe I have the kappa of ti, tj, times the kappa of tr, and this here is the kappa of ti, tr, and here I'm left with the kappa of the tj, and again you see this corresponds to distributing my 3 variables into groups. So here I say, okay, I take the I and the j together, but leave the other one alone, going in its own cumulant, and here I'm doing it that I and r, the first and the third, are going together, and the second one is alone. Okay, and then I have also the term which comes from here, if I put in for this expectation this term here. I mean, I already have used this term, but I still have this one. So if I plug this in, then I get here just the product of 3 kappa. So kappa of ti times kappa of tj times kappa of tr. And in this case, I just decide that each of the arguments should be for itself, has its own kappa. And I just have this decomposition of the set 1, 2, 3 into subsets. And I mean, those are all possibilities how I could distribute my my 3 arguments into different groups. Okay, and that's, so I mean, that's, so what you see here, in this case, if you go on, it will be the same. So this is actually the rule for how moments and cumulants are related. So, yeah, and maybe next time I will this then write down more explicitly in general, and then we also have to see, yeah, what kind of more information we get out from this description. But in principle, this cumulant expansion, this formula here, which you can see as a very analytic formula, has actually, if you plug in for your functions just monomials, it has a very concrete combinatorial meaning and interpretation by giving you a precise combinatorial relation between moments and cumulants. A very nice nature. I mean, the moments are given by summing over cumulants and products of cumulants, and the sum is getting bigger and bigger, but this sum has a very specific and a very clear structure. So you're summing over all those decompositions here, so partitions of the set 1, 2, 3, and each of them makes a very clear contribution in terms of cumulants. Okay, so next time I will, yeah, phrase this, write this down in general, and we will come back to this. But so I hope you have got the idea from this where all this comes from. Good? Okay, so that's it for today.